Quantum computing is a type of computing technology that leverages the principles of quantum mechanics to perform certain types of computations much faster than classical computers. Quantum mechanics is a branch of physics that describes the behavior of matter and energy at the smallest scales, such as atoms and subatomic particles. Some of the key principles of quantum mechanics that are relevant to quantum computing include superposition and entanglement. In simple words, a quantum computer is a type of computer that uses quantum mechanics so that it can perform certain kinds of computation more efficiently than a regular computer can. Let's understand this by example. How a regular computer stores information. Now, a regular computer stores information in a series of zeros and ones. Different kinds of information, such as numbers, text, and images, can be represented this way. Each unit in this series of zeros and ones is called a bit. So, a bit can be set to either 0 or 1. Now, what about quantum computers? A quantum computer does not use bits to store information. Instead, it uses something called qubits. Each qubit can not only be set to 1 or 0, but it can also be set to 1 and 0. A simple example for understanding how quantum computers work. Now, suppose you're running a travel agency, and you need to move a group of people from one location to another. To keep this simple, let's say that you need to move only 3 people for now: Abhishek, Balaji, and Chaitanya. And suppose that you have booked 2 taxis for this purpose, and you want to figure out who gets into which taxi. Also, suppose here that you're given information about who's friends with who, and who's enemies with who. Here, let's say that Abhishek and Balaji are friends. Abhishek and Chaitanya are enemies. Balaji and Chaitanya are enemies. And suppose that your goal here is to divide this group of 3 people into the 2 taxis to achieve the following 2 objectives. Maximize the number of friend pairs that share the same car. Minimize the number of enemy pairs that share the same car. Okay, so this is the basic premise of this problem. Let's first think about how we would solve this problem using a regular computer. Solving this problem with a regular computer. To solve this problem with a regular, non-quantum computer, you'll need first to figure out how to store the relevant information with bits. Let's label the 2 taxis taxi number 1 and taxi number 0. Then, you can represent who gets into which car with 3 bits. For example, we can set the 3 bits to 0, 0, and 1 to represent. Abhishek gets into taxi number 0. Balaji gets into taxi number 0. Chaitanya gets into taxi number 1. Since there are 2 choices for each person, there are 2 times 2 times 2 is equal to 8 ways to divide this group of people into 2 cars. Here's a list of all possible configurations. A, B, C. 0, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. Using 3 bits, you can represent any one of these combinations. Computing the score for each configuration. Now, using a regular computer, how would we determine which configuration is the best solution? To do this, let's define how we can compute the score for each configuration. This score will represent the extent to which each solution achieves the 2 objectives I mentioned earlier. Maximize the number of friend pairs that share the same car. Minimize the number of enemy pairs that share the same car. Let's simply define our score as follows. The score of a given configuration equals #friend pairs sharing the same car, #enemy pairs sharing the same car. For example, suppose that Abhishek, Balaji, and Chaitanya all get into taxi number 1. With 3 bits, this can be expressed as 1, 1, 1. In this case, there is only 1 friend pair sharing the same car, Abhishek and Balaji. However, there are 2 enemy pairs sharing the same car, Abhishek and Chaitanya, and Balaji and Chaitanya. So, the total score of this configuration is 1 minus 2 is equal to -1. Solving the problem. With all of this setup, we can finally go about solving this problem. With a regular computer, to find the best configuration, you'll need to essentially go through all configurations to see which one achieves the highest score. So, you can think about constructing a table like this. A, B, C, score. 0 is 0, 0, minus 1. 0 is 0, 1, 1, one of the best solutions. 0, 1, 0, minus 1. 0, 1, 1, minus 1. 1, 0, 0, minus 1. 1, 0, 1, minus 1. 1, 1, 0, 1 the other best solution. 1, 1, 1, minus 1. As you can see, there are two correct solutions here, 0, 0, 1 and 1, 1, 0, both achieving the score of 1. This problem is fairly simple. It quickly becomes too difficult to solve with a regular computer as we increase the number of people in this problem. We saw that with 3 people, we need to go through 8 possible configurations. What if there are 4 people? In that case, we'll need to go through 2 times 2 times 2 times 2 is equal to 16 configurations. With n people, we'll need to go through 2 to the power of n configurations to find the best solution. So, if there are 100 people, we'll need to go through 2 superscript 1 equals 1 0 superscript 3 equals 1 million 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 configurations. This is simply impossible to solve with a regular computer. Now solving this problem with a quantum computer. How would we go about solving this problem with a quantum computer? To think about that, let's go back to the case of dividing 3 people into 2 taxis. As we saw earlier, there were 8 possible solutions to this problem. A, B, C. 0, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. With a regular computer, using 3 bits, we were able to represent only one of these solutions at a time, for example, 001. However, with a quantum computer, using 3 qubits, we can represent all 8 of these solutions at the same time. So, instead of going through each of those potential solutions sequentially, we can compute the scores of all solutions at the same time. With this particular example, in theory, your quantum computer would be able to find one of the best solutions in a few milliseconds. Again, that's 001 or 110 as we saw earlier. A, B, C, score. 0 is 0, 0, minus 1. 0 is 0, 1, 1, one of the best solutions. 0, 1, 0, minus 1. 0, 1, 1, minus 1. 1, 0, 0, minus 1. 1, 0, 1, minus 1. 1, 1, 0, 1 the other best solution. 1, 1, 1, minus 1. In reality, to solve this problem, you would need to give your quantum computer 2 things. All potential solutions represented with qubits. A function that turns each potential solution into a score. In this case, this is the function that counts the numbers of friend pairs and enemy pairs sharing the same car. Given these 2 things, your quantum computer will spit out one of the best solutions in a few milliseconds. In this case, that's 001 or 110 with a score of 1. Here are some fundamental concepts of quantum computing. Qubits, quantum computers use quantum bits, or qubits, as the fundamental unit of information. Unlike classical bits, which can be either 0 or 1, qubits can exist in a superposition of states, meaning they can represent both 0 and 1 simultaneously. This property allows quantum computers to perform certain calculations in parallel. Superposition is a quantum phenomenon that enables qubits to exist in multiple states at once. This property allows quantum computers to explore multiple solutions to a problem simultaneously, potentially speeding up computations for specific tasks. Entanglement is a quantum phenomenon where the state of one qubit becomes correlated with the state of another qubit, even when they are physically separated. This property allows for the creation of qubit pairs with interconnected states, which can be useful for various quantum algorithms. Quantum gates. Quantum computers use quantum gates to manipulate qubits. These gates are analogous to the logical gates, and, or, not, etc., used in classical computing but operate on qubits in superposition. Quantum algorithms. Quantum computing algorithms are designed to take advantage of the unique properties of qubits, such as superposition and entanglement, to solve specific problems more efficiently than classical algorithms. One famous example is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms, posing a potential threat to modern cryptography. Quantum speedup. Quantum computers have the potential to solve certain problems significantly faster than classical computers. However, not all problems benefit from quantum speedup, and it depends on the specific algorithm and problem being addressed. Quantum computing is still in its early stages of development, and practical, large-scale quantum computers are not yet widely available. Researchers and organizations are actively working on overcoming technical challenges such as decoherence, which can cause qubits to lose their quantum properties, and error correction, to make quantum computers more reliable and scalable. Quantum computing has the potential to revolutionize fields like cryptography, optimization, material science, and drug discovery by solving complex problems that are currently intractable for classical computers. However, it is important to note that while quantum computing offers exciting possibilities, it will likely coexist with classical computing for the foreseeable future, as each has its own strengths and limitations.